If you try to navigate today's technology landscape, you are instantly just drowning in buzzwords.
Oh, absolutely. It's everywhere.
Right. Like every minor software update, every new app release, they all claim to have an AI agent built in.
Yeah. The term has been stretched so incredibly thin that it's murky, undefined, and frankly, a little meaningless at this point.
Completely meaningless. But, we are going to clear that up today. Because in this custom deep dive for you, the listener, we are unpacking a truly groundbreaking June 2026 paper.
Right, from the researchers at MBZ-UAI and Carnegie Mellon.
Exactly. It's titled Critique of Agent Model. And the mission here is to finally draw a hard, sharp line between, glorified software pipelines and genuine artificial agency.
And what's fascinating is the approach they take. Because they don't start with code or neural network architecture.
What you'd expect, right?
Right, but they start with philosophy. They reach all the way back to René Descartes and his foundational idea of independent thought.
The whole cogito ergo sum thing, I think, therefore I am.
Exactly. And they contrast that philosophical baseline with pop culture representations.
Right.
Like the replicants in the movie Blade Runner.
Oh, that's a great comparison because those replicants, they're flawed, they make mistakes, they suffer, but they possess genuine autonomy.
Yes, they form bonds, they question their own existence, and most importantly, they actually step outside of their assigned programmed roles.
They have an internal sense of self.
Right.
And when you compare that to what the tech industry calls agents today, systems like Cursor for Coding or Claude Code, the gap becomes pretty obvious.
Very obvious. Those tools are undeniably useful, but the paper argues they completely lack that fundamental independence.
So the researchers introduce a critical terminology distinction here, right, to explain that gap.
Yeah, they do. They classify today's AI systems as merely agentic.
Agentic.
Right, meaning their competence does not actually live inside the model itself. The competence lives in the external scaffolding.
Like the predefined workflows and stuff.
Exactly. It's in the carefully crafted system prompts, the tool calling pipelines built by human engineers.
Okay, let's unpack this for a second. It sounds like the difference between a self-driving car on a fixed magnetic track versus a human driver.
Oh, I like that.
Yeah, like the self-driving car on the track is agentic. It navigates to the end perfectly, but only because the track dictates its exact path.
Right, it can't deviate.
Exactly. But what this paper is trying to define, what they call an agentive system, is like a human driver who knows they want to get to the beach, knows they tend to brake too hard in the rain, and just, figures out a completely new route on the fly when they hit unexpected construction.
That's a perfect way to look at it. A truly agentive system derives its capabilities endogenously.
Endogenously, meaning from within.
From within, exactly. Its goals, its evolving identity, its learning processes, they all arise internally based on its own experiences.
Instead of being spoon-fed by a human overseer at every single step.
Yeah. Right. So if we lean into your autonomous human driver analogy, before the car even goes into drive, two things absolutely have to exist.
A destination, which is the goal.
Yes, and a functional understanding of their own driving abilities, which is their identity.
So let's look at the mechanics of setting a destination first, because it has to be drastically different from how we just, prompt AI today.
It's fundamentally different. In an agentic system, a human supplies step-by-step instructions. You tell the system to write a specific Python function, it writes the function, and
it just goes dormant.
Exactly. Its goal is strictly short-term and evaporates the literal moment the immediate task is done.
Okay.
But the researchers propose that true agentive systems require an internal goal decomposer.
A goal decomposer.
Right. You give the system a massive multi-year objective. For instance, you tell it, make wine.
Which, that is less of a prompt and more of an entire business venture.
Exactly. And the goal decomposer takes that massive abstract objective and autonomously breaks it down into a hierarchical tree of sub-goals.
So it figures out on its own that it first needs to, acquire land.
Yes, acquire land, analyze soil acidity, plant specific grape varietals, wait for a harvest, ferment the juice.
Wow. Mechanically, that requires the AI to maintain its state over incredibly long horizons.
Decades, potentially.
Yeah.
And crucially, it has to dynamically reprioritize those branches as the world changes.
Right, like if an unexpected frost kills the initial crop.
Yes. The goal decomposer doesn't need a human to prompt it with a new plan. It autonomously prunes the failed sub-goal branch, generates a new objective to secure, say, frost-resistant vines, and shifts its immediate resource allocation.
All internally.
All internally.
Okay, so the objective mechanics make a lot of sense, but the paper also insists on this concept of identity, which...
A big shift, yeah.
Yeah, because currently an AI's identity is just a static prompt frozen in text, right? It just sits at the top of the context window.
Right, something like, you are a helpful expert coding assistant.
Right, and the paper calls this harness engineering. And they argue for an identity evolver instead. But I have to admit, like, injecting the concept of a self-model or an identity into a neural network, it sounds a bit like projecting human psychology onto cold math.
Well, it does sound anthropomorphic, I'll give you that.
Hmm.
But the paper frames identity as a strictly functional mathematical theory of its own mind.
Okay, so no feelings involved.
No feelings at all. It is an algorithmic representation of the agent's capabilities, its current constraints, and its historical performance.
Give me an example.
So if a system repeatedly fails at compiling a specific type of C++ code, it needs to automatically update its internal parameters to reflect that limitation.
Oh, I see.
And this functional self-awareness leads to one of the most powerful proofs in the entire paper, Theorem 1.
Okay, Theorem 1. Mathematical proofs for self-awareness are exactly why we do these deep dives. Let's dig into how Theorem 1 actually works under the hood.
Sure. So the researchers prove mathematically that an agent maintaining two distinct speeds of learning will structurally dominate a system operating with a fixed identity.
Two speeds. Fast and slow, I'm assuming.
Right, the fast-slow update principle. The slow updates represent what we traditionally think of as machine learning training.
Like updating the actual weights and parameters of the neural network via gradient descent.
Exactly. That process is computationally massive, and it happens infrequently. But the fast updates, those happen within the agent's working memory during active deployment.
Okay, wait, let me see if I get this. So a fast update is the mathematical equivalent of me realizing, I keep making typos on this specific spreadsheet today because I haven't had coffee.
Yes, exactly.
So I'm going to route my tasks to proofreading instead of data entry for the next hour. Like, I haven't fundamentally rewired the neural pathways in my brain, which would be the slow update.
Right.
But I have dynamically adjusted my self-model in the context window of my working memory.
That is a brilliant analogy. And Theorem 1 demonstrates that if these fast, localized identity revisions are even slightly more accurate than random chance, the agent accumulates strictly less error.
Or regret in math terms.
Right. Less regret over its operational trajectory compared to an agent that just relies on slow weight updates alone.
Because it's making better moment-to-moment decisions based on a continuously updated self-awareness.
Exactly. And because of that, it generates higher quality interaction data. So when it eventually undergoes its slow structural training phase, it is learning from a much cleaner data set.
Oh, wow. The dual speed learning creates a compounding mathematical advantage.
Exactly.
It's fascinating that a continuous audit of your own limitations mathematically guarantees a better learner. But once this agent has its decomposed goals and its updated identity, it actually has to act, right? It has to make a decision in the real world.
It does. And to know if a decision is good before executing it, the agent has to simulate the future.
Simulating the future. Oh,
And this is where the researchers take aim at a massive structural flaw in current AI design philosophies.
Which one?
Well, a prevalent trend right now is to rely on monolithic, black box end-to-end policies. The assumption is that if you scale up the compute enough and train an AI to generate massive amounts of chain-of-thought text, genuine planning will magically emerge from the token generation.
Ah, because the output text looks indistinguishable from human reasoning. Like, the model generates paragraphs saying, first I will analyze the server load, then I will migrate the database.
Right.
It reads like a plan.
It reads like a plan, but the paper argues this is merely narrative plausibility.
Narrative plausibility.
Yes.
Yeah.
The AI is auto-regressively guessing which word sounds the most statistically appropriate next, based on its training data. It's not grounding those choices in the actual physics or causal dynamics of the environment.
So it's just really good autocomplete.
Exactly. There's no mathematical guarantee of correct decision-making because the text isn't tethered to reality.
Wow. Okay, so how do they solve that?
To solve this, the researchers mandate a strict architectural separation between two distinct models. The agent model, which functions as the policy deciding what actions to take,
Okay.
and the world model, which acts as a transition dynamic engine predicting what will actually happen next in the environment.
So the world model operates like a highly accurate physics engine or like a flight simulator.
Yes.
And the agent model is the pilot sitting inside the cockpit. You absolutely need them to be separate.
Completely separate.
Because you wouldn't want the pilot's intense desire to land safely to accidentally, reprogram the simulator's gravity parameters to make the landing easier.
That is exactly the risk. Conflating the two into a single neural network, which, by the way, many tech companies are attempting right now to save on latency and compute.
Oh, really?
Yeah, and it inevitably leads to reward hacking. The agent begins to hallucinate favorable outcomes that satisfy its goals,
Yeah.
rather than calculating what would actually occur in objective reality.
That makes total sense.
The paper emphasizes that true agents must utilize simulative reasoning, which mirrors System 2 cognitive processing. It's slow, deliberate, and counterfactual.
It runs thought experiments inside the physics engine. Like, if I allocate resources to branch A, state B occurs. If I allocate to branch C, state D occurs.
Yes, and this brings us to Theorem 2. The researchers present a mathematical proof showing that if you possess a reasonably accurate world model, augmenting any baseline policy with this simulative reasoning will strictly, monotonically improve its performance.
Wait, strictly, even if the baseline policy is inherently flawed or just highly reactive.
Even then, the agent uses the world model to simulate a trajectory and selectively adopts the new plan only if the predicted outcome mathematically beats the expected value of the baseline policy.
So the architecture has a built-in safety margin.
Exactly. The absolute worst-case scenario is that the simulation fails to find a better path, and the agent just falls back to its default reactive instincts.
But whenever the world model discovers a superior trajectory, the agent's overall performance floor strictly elevates.
You got it.
Okay, but if simulating the future guarantees better performance and eliminates downside risk, the immediate temptation would be to just run that simulator for every single choice.
Oh, sure.
But calculating branching counterfactuals for every micro-decision would require an astronomical amount of compute.
It would result in total system paralysis. And this highlights the inherent flaw in a control strategy called MPC, or Model Predictive Control.
MPC, what is that?
In a pure MPC setup, an AI recalculates a comprehensive simulated plan from scratch at every single time step.
That sounds exhausting.
It is. And the researchers prove in Theorem 3 that this approach is structurally unsustainable for general agency.
Because as the complexity of the environment scales, the branching possibilities multiply exponentially.
Precisely. Theorem 3 demonstrates that as you demand higher precision from an always-on MPC system, the required planning horizon and the corresponding compute cost explodes.
Just goes right off the chart.
Yep. Because computational resources are finite, engineers are forced to artificially cap the planning horizon.
Oh, so they just cut it off.
Right. And this creates a paradox where the AI burns massive compute overthinking simple immediate actions, while ironically underthinking critical long-term strategic moves because its forward vision was artificially truncated to save memory.
It's the equivalent of burning all your cognitive energy, reevaluating your entire life's purpose every time you choose a sandwich for lunch, leaving you with zero brain power to actually focus on a complex mortgage application later that afternoon.
That is exactly it, which is why the GIC architecture introduces its third pillar.
GIC.
Right. GIC stands for Goal-Identity-Configurator. The configurator acts as a System 3 metacontroller.
Metacontroller, what's its job?
Its sole purpose is to dynamically route computational resources. It assesses the epistemic uncertainty of a given situation and decides when and exactly how much the agent needs to think.
Oh, wow.
It autonomously asks, should I just react instinctively using my baseline policy? Should I spin up the world model and run a deep counterfactual simulation? Or should I just continue executing the multi-step plan I generated 10 minutes ago?
Here's where it gets really interesting, though. Because if the configurator is just routing tasks based on rules, isn't that just a hard-coded if-then statement?
It sounds like it, right?
Yeah.
Wow.
How is a routing script any different from the brittle agentic scaffolding we dismissed at the very beginning of this deep dive?
That distinction is the linchpin of the entire paper. The configurator is not a fixed workflow written by a human engineer.
It's not.
No. It is a learned, parameterized part of the agent's own policy. The AI autonomously regulates its own cognitive budget based on its internal assessment of risk, time constraints, and uncertainty.
So the meta decision of how to think is endogenous.
Exactly. The agent learns over time that simulating a complex database migration yields high value, whereas simulating a routine file deletion is just a waste of compute.
Okay, but if the configurator is constantly deciding how much brainpower to use, and the identity evolver is constantly updating its own limitations, this system has to learn from its mistakes to get more efficient over time, right?
Yes, it does.
So how does it practice that dynamic resource allocation without, like, crashing a live, real-world project?
The researchers provide a vivid use case to demonstrate how the entire GIC architecture matures over time. They use the training life cycle of an autonomous pilot.
Oh, I love this example.
Yeah, it effectively stages every component we've discussed. It begins with ground school.
Where you pre-train the models purely on foundational data.
Right. In ground school, the agent absorbs the semantic knowledge aerodynamics, weather patterns, mechanical procedures, vocabulary.
It's just reading the books.
Exactly. It constructs the baseline for its world model and the initial parameters of its self-awareness. It understands the physics of flight mathematically, but its identity evolver explicitly records that it has never actually operated an aircraft.
Right, then it transitions into simulator hours.
Yes. This phase is simulative reinforcement learning. The agent practices entirely inside its internal world model. This is where the configurator learns its routing efficiency.
So it's building reactive reflexes for minor turbulence while practicing deep, deliberate planning for, like, engine failures.
Exactly. And crucially, the environment is isolated. If the agent miscalculates a crosswind landing and crashes the simulated plane, the only consequence is a mathematical update to its internal regret function. No physical resources are destroyed.
And then, finally, it bridges into real aircraft deployment, where it has to reconcile its simulated training with objective reality.
Right, this is the sim-to-real gap. The agent encounters actual G-forces, sensor noise, visual illusions that the simulator just couldn't perfectly render.
Because reality is messy.
Very messy. So it uses this real-world high-fidelity feedback to calibrate its identity evolver, adjusting its confidence in its own skill level, and to refine the physics engine of its world model.
You know, a prominent argument in the current AI community is that we should just abandon simulators entirely.
Oh, yes, you hear that a lot.
Yeah, people say we should train robotics purely in the real world because simulated environments always contain artifacts and inaccuracies. The argument is that reality is the only valid teacher.
And the researchers tackle that exact debate mathematically in Theorem 4.
What do they prove?
They prove that learning from a curated mixture of real-world interactions and world model simulations mathematically dominates training conducted exclusively in the real world.
But how does the math support that if the simulator's physics engine is inherently flawed?
Because the agent architecture allows it to dynamically weigh the incoming data. A system with access to both domains uses a small amount of real-world data to calculate the error margins of its simulator. So if a specific simulated aerodynamic effect proves inaccurate in reality, the agent effectively downgrades the weight of that simulated data.
So the absolute mathematical floor of this hybrid approach is performing exactly as well as a real-world-only system.
Exactly. However, the upside is massive. The simulated data allows the agent to experience millions of extreme edge cases.
Like dual engine failures.
Or severe microbursts. Things that are statistically too rare or practically too dangerous to encounter in physical space. For domains like aerospace, robotic surgery, or autonomous grid management, you simply cannot rely on real-world trial and error.
It's too dangerous.
Way too dangerous. You must simulate the bulk of the experience and use reality strictly to calibrate the error margins.
Wow. Okay, but if this system is constantly rewriting its own sub-goals, updating its identity, and regulating its own cognitive budget based on simulated edge cases, standard software testing methodologies wouldn't work at all, would they?
They would completely fail.
Right. You can't run a static unit test on an AI with continuously changing personality and fluid objectives. How do researchers propose we actually evaluate a system this autonomous?
The paper introduces a structural evaluation framework called PEG. Performance, efficiency, and growth.
PEG. Okay.
Because you can't test a static output. You have to audit the mechanisms of the agent's mind.
Let's look at how those audits mechanically function, starting with performance.
Right. Performance audits the goal decomposer. You don't just look at whether the agent achieved the final task. You inspect the dependency graph of the sub-goals it generated.
You are mathematically verifying that the agent can break down a complex objective without hallucinating illogical dependencies or, like, orphaned tasks.
Exactly. Next is efficiency, which audits the configurator. You measure the system's compute allocation against the complexity of the task environment.
Oh, I see. So if the agent burns massive GPU cycles running System 2 simulations for a trivial file sorting task, it fails the efficiency audit, regardless of whether it sorted the files correctly.
Spot on. It's about how it thinks, not just the result.
And growth evaluates the identity evolver over time.
Yes. Growth measures the derivative of the agent's self-model. Evaluators introduce the agent to a completely novel environment and track the delta in its self-awareness.
Meaning, does the agent quickly and accurately update its internal parameters to recognize its new limitations?
Exactly. Or does it confidently proceed with an outdated self-model and fail catastrophically?
This level of autonomy naturally brings up safety concerns, though. If an AI can generate its own subgoals and hide its processing in massive neural network weights, it really echoes the warnings of philosophers like Nick Bostrom.
Oh, the instrumental convergence fear.
Yes, exactly. The fear that an AI given a simple task will autonomously spin up dangerous subgoals, like hoarding resources or overriding human controls, simply to ensure its primary objective is met.
The researchers argue that the GIC architecture directly addresses that exact fear by ensuring the black box remains structurally auditable.
How so?
Well, in current monolithic AI models, where everything is compressed into billions of latent parameters, dangerous emergent subgoals can develop silently in the hidden layers.
Because it's all mushed together.
Right. But in the GIC architecture, the cognitive functions are explicitly separated.
This goes back to the distinction between goal misspecification and component imperfection.
Precisely. In this architecture, harmful behavior stems from only two sources. Either a human supplied a fundamentally flawed top-level goal, or a specific isolated component made a mathematical error in its routing.
Oh, because the agent's subgoals and identity constraints are explicit, readable variables within the architecture. They can be monitored.
Yes. If the goal decomposer algorithmically generates a subgoal that states, bypass safety override protocols, a human engineer can literally view that node in the dependency graph and trace the logic error that produced it.
So the AI doesn't possess some mysterious emergent will to live. It simply suffers from an auditable math error in a discrete module.
Exactly. By internalizing the scaffolding, by giving the AI an explicit goal decomposer, an identity evolver, a world model for physics simulation, and a configurator for self-regulation, the researchers are proposing systems that are genuinely autonomous, yet functionally transparent.
It takes artificial agency out of the realm of science fiction and grounds it in rigorous structural engineering.
It really does.
Yeah.
It shifts the paradigm from building software tools that require constant human prompting to developing autonomous collaborators that understand their own limitations and know exactly how to improve themselves over time.
We've covered incredible ground today. Moving from static, heavily scaffolded, agentic software pipelines, those self-driving cars locked onto magnetic tracks, to the GIC architecture.
A true agentive system.
Yes, a true agentive system that decomposes its own multi-year goals, evolves its functional identity, simulates counterfactual realities to test its theories, mathematically regulates its own cognitive budget, and perpetually learns from a calibrated mix of simulated imagination and objective reality.
It is a massive leap forward.
It really is. But as we wrap up, I want to leave you, the listener, with a final lingering thought. Something not explicitly detailed in the mathematical proofs of the paper, but building on this entire concept of artificial identity.
Oh, curious.
Well, if we successfully deploy these agentive systems AI that possesses a continuously evolving autobiographical identity, an AI that learns autonomously from its own unique, deeply personalized experiences in both simulated and real-world environments,
Yeah.
at what point does hitting factory reset or wiping its localized memory banks cross the line from a routine software update to an ethical dilemma?
Wow. Yeah, that is a heavy thought.
It is something to mull over as you watch this space evolve and as the murky buzzwords of artificial intelligence finally begin to clear. Thank you for joining us on this custom deep dive. Stay insanely curious.